about modeling multiple M2 branes.
Okay, so thank you very much. I'd certainly like to thank the organizers for running this workshop and for inviting me and giving me this opportunity to speak. So this is work which started in a paper a year ago with John Bagger, but we have some new results which we're quite excited about, which we should appear very soon, i.e., well, a day or two. And I also referred you to a paper by Gustafsson later on in the talk. Right. So just a quick summary of what I'm going to talk about during the talk. So of course, start with an introduction, explain what we're interested in, why we're interested in it, and then I'm going to have a discussion of the supersymmetry. So this is a specific supersymmetry, how it works in 11 dimensions, and how it might apply to M2-branes. And so we're going to propose a form for the supersymmetry algebra, if we like a realization of the supersymmetry algebra, on the fields of M2-branes. And the main result that's come out recently is that this algebra can be made to close on 16 supersymmetries. Whereas last year we reported that we couldn't close it, now we can, once you take into account a local symmetry. And if I have time, and if you're still willing to listen to me, as a section on mass deformations, related to some work done by Benner many years ago, where you turn on some background flux. This induces a mass on the M2-branes, and as a result, you get a Myers type effect where the vacua correspond to fuzzy M5s. So M5s wrapped on a fuzzy S3. And that's reproduced by the model that we have here. And then, of course, I will end with some conclusions and comments. So M-branes are mysterious objects, right? We've studied D-branes a great deal in string theory, and we have a microscopic description of D-branes given by Polchinski and the open strings that go between them. And this, I mean, you cannot overestimate the importance of that knowledge in the study of string theory in the last 10 years. In contrast, M-branes, very little is known. Even if you take a single M-brane, you can get some pretty remarkable results using duality coming out. So a single M-brane is, of course, just described by having some object with a particular tension, and his action is the surface area, possibly plus some other stuff. The other stuff, in the case of the M5 brane, of course, is this mysterious two-form gauge field. And in the M2 brane, there isn't any other stuff except perhaps the fermions. So the equations of motion for these single branes were known long ago. Berkshire and Townsend, I think, and Sezgin, I think they're the first people to talk about the M2 brane, kappa supersymmetry and everything. The M5 brane was much later, 10 years later. House, Sezgin, West had the first covariant formulation. Schwartz and Perry had the first equations whatsoever. And then there's this action formulation of Pasty, Stoke, and Tonin. But that's just a single M-brane, and multiple M-branes are more or less completely unknown. I mean, of course, some things are known, but there certainly isn't such an understanding as there is for D-branes. And I'll list some things that are often said, which may or may not be true, of course. There's no known Lagrangian description. Well, it's possible at the end of this talk that that's no longer true, that we might be able to give you a Lagrangian description, although that's still somewhat speculative. Part of the justification for that is the statement that there's no small parameter for perturbative description. So, of course, the fact that there's no small parameter doesn't mean there isn't a Lagrangian description, but of course, it allows you to say that if there isn't a Lagrangian description, that's not a contradiction. And then the M2 brane and the M5 brane have these peculiar scalings with the number of branes. So the M2 brane, the number of degrees of freedom is supposed to go like n to the 3/2, and for the M5 brane, it goes like n cubed. So these can be obtained from ADS CFT type arguments by counting entropies. So a lot of what's known about these theories, of course, comes because they have ADS duals, ADS 4 cross S7 and ADS 7 cross S4. But our approach was just to say, well, you know, if it's a geometrical object and there's lots of geometry underlying branes, then still one might hope to say something, to derive things from some sort of geometrical principles. So I would like to just say, you open your mind, and we're going to proceed and see how far we get. And I think there's certainly some new results here which are encouraging. So the starting point for us, for me at least, I can't speak for John, was that this paper by Basu and Harvey, which is a curious little paper from a few years ago, in which they considered a BPS state of n coincident M2 branes ending on an M5 brane. So there's the M5 brane, and it comes in like this. And they proceeded more or less in direct analogy with the classic example in D-brane physics, where you have a D3 brane and a D1 brane coming in. The D1 brane ends on the D3 brane, and it produces a BPS monopole on the D brane. So this story goes back to the early days of D-brane physics. Here's a beautiful picture of it for your viewing pleasure. You need to have a large number of D1 branes. Well, for what I'm going to say, you need to have a large number. They induce a magnetic flux that goes up into the D3 brane. And of course, on the D3 brane, that's described by monopole. On the D1 brane theory, you can view it as a fuzzy funnel. So you can look at the supersymmetry equations on the D1 brane, which is just like a half line. You could derive this NARMS equation as the BPS equation on the world volume of the D1 brane. So this is studied by Diaconescu, Constable, Myers, Taffiord, and who else? Dimitri Simpis. And there you get the following picture. So in some sense, you remove the blue D3 brane, and then the D1 branes all blow up into an S3, a fuzzy S3. Now, from the point of view of M theory, if we look at M2 branes and M5 branes, well, an M2 brane ends on an M5 brane, and years ago, I wrote down with Howe and West the world's volume Salton for the self-dual string that you get there. So it has a one-dimensional intersection now, and then four transverse directions. But Basu and Harvey's idea was to try to see what it looks like from the M2 brane world volume, and they proposed a BPS equation like that. So on the right-hand side, there's something that's cubic in the x's, and it's constructed out of this quartic thing, which is a Nambu bracket, which is all cyclic combinations. So this has been studied by various people. Dave Berman, for example, his student, and some guy, Nogradi. And it does live up to some expectations about what you'd want this equation to do.
What's G?
Yeah. So in their example, G is just a preferred matrix. It's this explicit matrix that they give. So you can ask a lot of questions about this. Because actually, if you start, the more you think about it, the less meaningful this equation becomes. Because you think you know what x is, and they're certainly assuming that x is a matrix. But nobody knows what describes the coordinates of a multiple M2 brane. So it's not just simply a matrix, but maybe you can model it by a matrix. And the thing on the right-hand side is cubic, but it's constructed out of something with 4 objects. We'll come back to this later as to how to interpret this. But for them, G is a specific matrix. These are all matrices, and G is a specific matrix. I can be very explicit about it. Okay. So geometrically, this fuzzy funnel that you get is very similar to the fuzzy funnel you get from a D1, D3 brane case. They're able to solve this equation and construct things that look like fuzzy S3s now. So actually, Sanjay's work was very important here. So you're constructing fuzzy odd spheres, particularly S3, as representations of matrices that satisfy, well, if you just strip off the derivative, you get matrices that satisfy that sort of algebra. So, of course, the only difference is it's extended along the x1 direction. Well, that's not particularly interesting. It's a fuzzy S3, and the sphere radius goes like 1 over the square root of the x2 coordinate. So one of the questions we posed was, well, where the hell does this equation come from? So what we did last year was to derive it from sort of geometrical and supersymmetric principles, or try to at least. So we argued that the scalar fields of the M2 brane take values in a non-associative algebra, as opposed to a matrix algebra. So I'm going to review this construction in a moment to explain why we thought that. I don't want to, well, let me not say anything right now. What we were able to do was write down some supersymmetry rules, partially, in which the Basu-Harvey equation comes as the BPS equation. And this particular form that you asked about arises as what we can call the anti-symmetrized associator in a non-associative algebra. So it was explicit construction and try to attempt to understand how this equation might arise. But we could only realize 4 supersymmetries. And we sort of said, and even I didn't really believe it at the time, was that, well, there's a novel gauge symmetry. We didn't understand how that worked. And if we ever did, then everything would work out. Well, now I'm happy to report back to you that we understand the gauge symmetry and everything works out. So we're going to study what I guess I'd call a realization of the M2-brane supersymmetry algebra. So I'm going to present to you a supersymmetry algebra for non-abelian x coordinates consistent with 16 supersymmetries and an SO8 gauge symmetry in 11 dimensions. So as I've said before, closure implies a novel set of gauge transformations, and if you do introduce the appropriate gauge field, this will allow you to close the algebra. So I should mention that very related work was done by a guy called Gustafsson a few weeks ago. His paper, unfortunately, has 5 versions at last count. The first version doesn't report failure, and the 4th version reports success. So he was definitely the first guy to do it. And John and I have a paper coming out any day, please, God, please. So, of course, once you have the algebra, you only have on-shell closure. You've got too much supersymmetry to have off-shell closure. So you're going to get the equations of motion, and these will come from an action. And the action we'll propose, which is it's like a twisted Chern-Simons theory. And we write it down, but it's an interacting 3-dimensional field theory with 16 supersymmetries and an SO8 R symmetry. The other novel thing which you would expect from the M2-brane is it has no free parameters in it. Okay.
The statement that 16 supercharges implies super Yang-Mills in all dimensions.
That's just wrong.
Incorrect.
Yes.
And this is the first example.
This is the first example I know of a theory with 16 supersymmetries with no gravity, and it's not Yang-Mills. I mean, it's got a gauge field in it, but it's Chern-Simons.
It's not super.
It's twisted Chern-Simons. Okay. So consider the supersymmetry transformations of coincident D2-branes. That we do know. This is described by Yang-Mills gauge theory. And here I've written down the transformation laws. One important feature of these laws is that epsilon is preserved by the brane, so it has this chirality projector on it. And psi is like the Goldsteinos, and so they have the opposite projector. And I say this because a lot of the reason why the gamma is there, in particular the gamma 10, is to ensure that that's preserved by those equations. So what we wanted to do is somehow lift this to a system with 8 scalars and an SO8 R symmetry and no dynamical vector, because that's what you expect from an M2-brane. In the abelian M2-brane case, you have the vector field, an abelian vector field. You simply dualize it, and you get, in 3 dimensions, you can dualize a vector to get a scalar, and that's how you get your scalar. And, well, it's hard to do non-abelian dualization, and you might just try to guess the answer and try looking it down. I think this was first studied by Schwartz. He didn't have any success, but he did look for Chern-Simons type theories. So anyway, the upshot of this is you want to guess something, so we guess the following thing. There's not much you can say for the x's, that's pretty much fixed. The fermions, you have the standard kinetic term, and then, well, you need something with 3 i's here. If you like to reproduce this. Or the other reason is because of this condition. You need there to be 3 i's to keep these opposite chiralities. So you've got to have something with 3 x's, naively, and some constant kappa. So the question is, this is just some totally antisymmetric object. Where's my... and we're going to figure out what it is shortly. Well, you can see immediately that if you look at the BPS equation for the M2-branes ending on M5-brane, then you're going to get this kind of equation, Basu-Harvey type equation. And it's always going to give you this kind of behavior that x goes like 1 over the square root of x2 from this equation, which if you invert that, x2 goes like 1 over r squared, which is the correct fall-off you want for a self-dual string. Right? But the scalar field goes off like 1 over r squared in 4 dimensions. So this is just a rough sketch of how you're going to land on such an equation, and there were basically 2 ingredients that got you there. you needed a cubic term in the x's in the supersymmetry algebra to get this cubic term here. And you needed to have gamma ijk for the supersymmetry, because that's what converts in the background. Gamma ijk converts into epsilon ijk. So gamma ijk is epsilon ijkl gamma L in this background, and that's what allows you to cancel the kinetic term with the cubic term. So although it's not clear what you
There must be a reason that equation doesn't work, because it's simpler than the Basu-Harvey equation, so they must have.
this.
Yeah, there's no G.
Yeah, so this is what our first paper was this. So yeah, what is this cubic thing? Well, let me go on. So you go back to your D-branes 101, and you're sort of like, well, the first thing you'd want is that there's going to be a central element, so that if you shift all the x's by an overall translation, nothing happens. And this would mean that you want to construct x in terms of commutators, because that's what you do in the Yang-Mills gauge theory. But the problem with the Yang-Mills gauge theory is this is a Jacobi identity and it's vanishing. So you can't construct it out of a Yang-Mills gauge theory. So that was where we had the naive idea that the x's, nobody ever said that the x's of M2-branes take value in an associative Lie algebra, so matrix algebra to be more exact. So you just say, okay, they don't take values in a matrix algebra, at least the standard one, and they take something that's non-associative, and then you can construct this. And that's what we did. So you could define the associator here, which is a common construction. So you've got to keep track of your order. And then you can define the square bracket to be the anti-symmetrized associator. And what we did in that paper last year was to provide an explicit example of a non-associative algebra for which this gives you precisely what Basu and Harvey had with that G, xi, xj, xk.
You have 8 x's.
8 x's.
You just take them to be the octonions and stuff?
You could try to take them, yeah, that would. But, well, okay, but they have another index, right? This is just, this I is labeling the transverse coordinates. Whereas when you think of the octonions, you'd express each one as being an octonion itself, right? Like x1 is an octonion, x2 is an octonion, and x3 is an octonion. Or
No, I guess so.
they're all equal to the same octonion. Well, then it would give you 0. Like the octonion is an algebra with a basis of 8 generators.
Yeah.
And xi just happens to have 8 different scalar fields, but you don't want to set each one separately equal to, well, you could, but I don't think that would work in general. Okay. Well, that was last year, and this is this year. So what's going on? So we motivated everything by thinking about this non-associative algebra. So I don't know, there's this nice quote. I wish someone could tell me it. I think it's by Wittgenstein, about using words as a construct, like a ladder, to get to a certain place. Then once you've got to the place, you can discard the ladder, and the concept exists independently of the words.
That's Wittgenstein, end of the Tractatus.
Okay, very good. I knew it was something in Cambridge would know. Well,
It's the last phrase of the Tractatus.
No, it's not the last phrase, because the last phrase is that which we cannot speak, we should not.
Oh, okay, whatever comes.
That which we do not know, we cannot speak. Anyway, it's a lovely word.
Last but one phrase.
So I'd like to have him I would like to say to you now, well, forget what I've just told you. That might be over-dramatization. I've used it as a ladder to get somewhere, and let's start again, where I am on my little perch. Okay? What we really need is some kind of algebra, in quotes, which admits a totally antisymmetric trilinear product. And, well, because it rhymes with Lie, I've called it a 3 algebra. It's in the literature, there is some mathematical literature, and they call them tri-algebras. Maybe one other person's called them 3 algebras, I don't know. I'm calling them a 3 algebra. And my next paper will be B algebras, but we won't go there. So that's what we really need. Forget that it's defined as the, well, it's not important that it comes as the anti-symmetrized associator or anything like that. The other thing I would say is it's not important that it's actually an algebra. I only need that it has a triply antisymmetric trilinear product. I don't need it to have a normal double product. So it's not necessarily an algebra at all, right? Okay. So we're going to go back to our supersymmetry algebra and have this form in it. So let's look about this closure and this local symmetry. Well, if you look at a D2 brane, you look at the supersymmetry of the Yang-Mills theory. Perhaps I should just remind you what that is. There it is. So this is the supersymmetry. If you close this, if you try to close it particularly on the x, well, let's just look at closing it on the x's. So you take the commutation. And remember, this is the answer that we're going to try. So, yeah. Whoa. Woo. There we go. So you close it on the x, you always find this in the Lie algebra. In the gauge theory. So you get translations, and you get this commutator term, but you interpret the commutator as a gauge transformation. Right? You stick the lambda inside the brackets, and you just call this space-dependent gauge transformation. So if we do that in our model, well, you get something very similar. So if you want to interpret this as a gauge symmetry, you have to think of it in the following way. Delta x is generated by, has in some sense two generators, alpha, beta. And you stick them into this triple product with x. So the symmetry is generated by pairs of elements of the algebra, or the three algebra as we call it. Okay. So that's what we ignored last year. And that's what we're going to have to take seriously this year. So we want to understand that symmetry, how it arises, and how you can make it fly. Well, first thing is just to view it as a global symmetry. Forget the fact that it's gauged. So what do we need to do? So if we're going to construct an action for this theory, the first thing you're going to need is some kind of trace form, because ultimately these things are living in an algebra, and the action is just a number. And you're going to want to write down a kinetic term of this form, trace dx dx. Right? So a trace form is a symmetric bilinear product on the algebra into, say, the reals. I'm just connecting it to be the reals. I mean, it's, in a matrix algebra, it's trace AB. I don't have to tell you what it is. But more generally, it's something that satisfies this symmetry property. And you also typically want some definition of complex conjugation in the algebra, Hermitian conjugate, such that this is positive definite in that sense. And then you take all your x's to be Hermitian. And so this would make a good kinetic term, positive definite, and all that. Now, invariance of the Lagrangians tells you that this is what you want. So in other words, another way of saying that is that the symmetry preserves lengths, because think of trace AA as length. Well, this follows for us if you have this relation. Now, this may look a little odd, but it comes from another relation which is popularly used. Another condition people take of the trace is that it's what's called the invariance property, that A dot B times C is the same as A dot BC. So this is certainly true of matrices. And if you had this, and if you construct this as the anti-symmetrized associated, then this follows. So we want that condition. Okay, that'll make your kinetic term invariant. But we're going to have to add interactions. And various interaction terms where you have higher order polynomials, well, they will be invariant provided that the symmetry acts as a derivation. So that means that delta on some triple product is the sum of the various deltas on each term. And if you work this out, you get this thing, which is, I'm not the first person to talk about this. This is called the fundamental identity. It's appeared in several places, all sort of scattered about the literature. But for example, if you're in a Lie algebra, there's an analogous condition, which is that you just drop the beta and you have a double product, that this acts as a derivation, and that is the Jacobi identity. So this is the natural extension of the Jacobi identity to whatever these three algebras are. Okay? And this underlies everything. If you don't have this, nothing I say that in the future slides will follow. It's the key equation. Well, I guess, yeah. Definitely.
Sorry, what are alpha and beta?
So here they're just generic elements. Because the symmetry is generated by taking two objects, alpha and beta. And then you put that into your triple product, and that gives you a map on the algebra to itself. So they live in the algebra just like x, y, and z. Because they're acting on the x's. I just call them alpha and beta. Okay, so if I have those conditions, then I have a local symmetry. Sorry, I have a global symmetry of various Lagrangians I can write down using traces and this triple product. So for example, the potential we want is going to be the trace of the triple product with itself, so a sixth order thing. And that's going to be invariant under the global symmetry. Well, you can gauge this symmetry. Perhaps it looks a little odd, or I don't know, perhaps somebody here has seen something similar. But actually, the gauging works just as it would for any symmetry, just as it would for Lie algebra. So let's to help us out, because I don't understand exactly what's going on in these algebras. Just introduce a basis of the algebra. So here n is not the number of M2-branes, it's just the number of basis elements of this algebra. And so I introduce the analog of the structure constants. Ta, Tb, Tc is F, A, B, C, D, C, D. And I represent the trace as this matrix, this metric. So now I've got these, in some sense I've replaced the algebra with just these numbers, these simple numbers, these structure constants. So the fundamental identity is this relatively nasty combination of f's. But it's got that interpretation I gave you before, that the symmetry is acting as a derivation. And that invariance condition I mentioned tells you that if I raise the index on f, then f is totally antisymmetric. So this is completely analogous to Lie algebras, where you have a triple product. F's got 3 indices. There's the Jacobi identity has got 3 terms in it, and if you raise the index on the structure constants, everybody knows that that's totally antisymmetric. So it's a straightforward generalization in that sense. And the symmetry that we want can now take this form, where I have this lambda which has 2 indices. So this is the infinitesimal generator. Okay? So this is the thing that is a symmetry, and this is what we want to gauge.
Neil, is there a charge associated to this? If you have it just as a global symmetry, then do you then have a conserved charge?
Yeah, you'd have a conserved charge. Yeah.
How do you interpret that?
No, I don't know how you'd interpret it. But certainly it's a symmetry, so you have a conserved charge. At the end of the day, this isn't fancy. It's just you've got some tensor with some indices. And going to construct a Lagrangian, which is invariance property.
To generate a transformation of the x's, you need 2 objects, don't you, to put in something
To generate a transformation of the x's? Yes, right. So now this is what I previously called alpha and beta would be alpha A, beta B. So lambda would be alpha A, beta B. Right? Shall I write?
In terms of David's question, does that mean there are 2
That's what I'm trying
charges
to understand.
associated to each symmetry?
Well, think of it this way. The symmetry is generated by an object with 2 index structures. So yeah, there's n minus 1 over 2 possible generators. Right? But at the end of the day, I had this. This is what I started off with. In this notation, it's just that. That's just going into this basis notation. And actually, I've slightly allowed myself to be more general. It's not more general because it's a linear thing, so I can take linear combinations. So actually, I really should just write this as something lambda. Right, where lambda is an arbitrary antisymmetric object. I mean, in a gauge theory, these would be you would have just one index. It's sort of Lie algebra. You'd have just one index, and these would just be you expand the group element in terms of.
I think the point is here the charge won't live in the algebra because it's always made up out of products.
Yeah, I don't know how that. Yeah.
Whereas in the Lie group, the charge is in the joint. Here it will be something different.
Yeah, these are actually interesting questions, and I have to say I'm a little embarrassed because I haven't been trying to figure out what these mean in terms of these algebras and yet. So cause you can't exponentiate them and get group elements naively. I don't know how that's working.
But so in a usual field theory, you would have one charge, and that would generate the symmetry.
Well, you don't have
Two
one
charges
charge.
to
You have
generate
one
the
charge
symmetry.
for each dimension of the of the group, right?
Yeah, let's say I just happen to be taking
Yeah.
one
If you just have a U1, then you've got one charge.
Right, so now here you get two charges associated with U1.
Well, suppose you had n generators, then you get n minus 1 over 2 charges. Because it has to be antisymmetric. So you,
Right, just one generator, that's minus
well, you can't do it because it has to be antisymmetric in the generators. So one isn't big enough. I mean, the smallest, perhaps I've got a slide later on, but the smallest non-trivial 3 algebra has 4 generators because you want to have this relation. Obviously, you need at least 3, and then this condition where it says it's totally antisymmetric means you can have 4. It's just like the smallest non-trivial Lie algebra is SO3, or SU2, or whatever you want to call it, but where f is epsilon. So here the smallest 3 algebra's got 4 generators, and as such there are 4 choices for A and B, and hence there are 4 times 3 over 2 choices for lambda, and that's how many charges you'd have. In fact, in the smallest, well, I can come back to that later. It does not worry. So we want to gauge this, so we're going to go the textbook way. Just part of the reason it took me so long to do this is because I thought it was a weird stuff, but actually it's just dead common. So you define capital D in this manner. It's just analogous to Lie algebra. So now A sits in this tensor product, antisymmetric tensor product. And gauge covariance tells you that this defines d mu, that delta A transforms as d mu lambda. So this gives you a gauge covariant derivative.
So sorry, so the A's are this complex number? Will not be
Capital A?
to algebra.
Capital A lives in, capital A is something from the algebra point of view which is in the tensor product, antisymmetric tensor product of the algebra. Right? So it,
But then how do you define the multiplication between A and X?
right. So A, where can I write? Oh, over here. What's really happening? So I've got this kind of old-fashioned, this clumsy notation perhaps. So X is in the algebra, and then you have this triple product. And if you take 2 elements of the algebra, then you can generate a linear map from the algebra to itself. A is living in the space defined by this, of linear maps. So this is the analog, well, for lack of a better word, you can call it the ass, it's the analog of the adjoint map. But now you need 2 elements of your algebra to construct an element of that. Well, okay, let's be polite. So this is the analog of the adjoint representation. And that's where A is living. In fact, A is going to, well, in the one concrete example I have, A is just an SO4 connection. But we'll get to that. So yeah, if I'd like to understand these algebras better and have a clearer picture and not rely so heavily on this index structure. But for now, please let me have this indulgence. So I've got my A, and this is a normal gauge covariant derivative. And of course I can construct my F in the same way, and F has a nice transformation property, as you'd expect. So everything's working just as it would in Lie algebra. So let's return to the supersymmetry algebra. So this is what we proposed, the top 2 lines. Here I've just put in the gauge covariant derivative here. And here I've replaced the triple product with this F. And then I have a gauge field now. And there's a natural choice for what the symmetry transformation is on the gauge field. Right? I mean, given the field content that we have. This is a natural. Okay. It's a bit odd because it's quadratic in the field, and maybe one can find some kind of auxiliary fermion to go in here. We haven't been able to do that yet. But the beautiful thing about that is this closes. I have to say it's absolutely astonishing, because without the A, you get a mess. With the A, you find only one condition: kappa has to be minus a sixth. And everything closes to this, on shell. So this was something very similar, at least, appears in this paper by Gustafsson a few weeks ago, the 4th version or whatever. He's got a slightly different take on the algebra, which is very interesting. Perhaps more fancy than what I've been using. I suspect that they're the same algebra, the same construction. because I can't see how you could do anything but what we've done.
Sorry, Neil.
Yeah.
In the original Basu-Harvey, I
Yeah.
don't think you said this, but the kappa actually had a thing that depended on n. Went like 1 over root n.
Yeah, well,
So if you fix,
that's not necessarily true. I can talk to you about that afterwards. The thing is, you don't know about these 3 algebras. You don't know what their representations are. So you simply, when you take a large n limit, they have a specific example, but I'm not sure that those actually are 3 algebras. The way I've defined it, I don't know if they satisfy the fundamental identity. So I can talk to you about it. Yeah, they had. If you want to do Basu-Harvey and get the right value for the energy, what Dave was referring to is that this kappa isn't just minus the 6. It seems to depend on various things, but the number of branes. But I have some hesitations about those calculations.
What filter equations are you using?
Right, we'll come to that. So this closes on these lovely sets of transformations, translations with gauge transformations. And there's apparently no free parameter. Actually, when I say it's no free parameter, actually, one thing I've realized last day or so is you can add a mass term to this.
So you have 8 x's
8 x's.
and 4 Majorana.
No, psi here is actually a 32 component spinner with 1 projection on it. So these are 11-dimensional notations. These are 11-dimensional gammas. So psi here is 16. So 30
8 Majorana fermions.
on shell.
That's all you're at.
It's 16 Majorana fermions off shell.
Propagating degrees of freedom don't add up.
Not off shell. On shell, it's 8. It's a classic thing of supersymmetry, right?
Yeah.
Off shell, the fermions have double the number of degrees of freedom as on shell.
Sure. So we've got 8 scalars.
8
plus-
scalars.
Plus a photon.
The photon will have been non-dynamical. Let's show you. So these close. So what are, that's this question. These are the equations of motion. So to close, they don't just close, you have to impose a fermion equation, which is this. And you have to impose a vector equation, which is this. Now you can ask yourself, supersymmetry will tell you what the boson equation is, and it's this, with this potential, as advertised, the square of the triple product. So this is the complete set. So these sets of equations of motion have 16 supersymmetries and a SO8 R symmetry. And apart from adding a mass term, I don't think there's any tunable parameter. So you can construct a Lagrangian for this theory. So this is just, it's invariant under the supersymmetries. And here it is. So kinetic term for the x's, kinetic term for the psi's. Here's your sort of Yukawa type term, the potential. And then you have this sort of Chern-Simons term. But it's not a straightforward Chern-Simons term. It's twisted by this f with tensor in it. So it's not naively something you would have guessed. But in summary, here you go. It's got the 16 supersymmetries and the SO8R symmetry. So it's gauge invariant, but the gauge field's non-dynamical because of the Chern-Simons term. So on shell, the degrees of freedom are just 8 x's and the fermions, which on shell are 8 Majorana fermions.
and just so I understand this notation, in terms of your trace structure that you had before,
Yeah.
if you write it in terms of traces, it's obvious that the top lines have got traces. That Chern-Simons term, is that a trace of?
Yeah, I don't know, because one of the reasons why I've gone to this notation is I don't know what the nice form is for things that have double index. So they're things that live in this ass.
Yeah.
So
I'm asking if you can trace your ass, I suppose.
well, I'll show you later. These are things that I'd love to.
Yeah.
I mean, I have to say.
Do this privately.
Do this privately. I think this. I have to say, I think there's some beautiful structure going on here. I mean, certainly this pops out. It doesn't. You don't force this. It just falls off the page. It's just. It's really. It's just striking. Now, so hopefully that would mean there's something interesting about these 3 algebras. But I actually only have one concrete example. I've got one concrete example, which I'll show you. And the other example where this works is an infinite dimensional example, where you take the Nambu bracket, you look at diffeomorphisms on R3. But I'll come back to that later. Okay, so this Lagrangian, it's certainly, it doesn't look that weird. This is kind of strange, and don't ask me about the global features and whether or not, it's well defined on the manifolds with boundary and all that. But this theory is classically conformally invariant. These symmetries, twisted Chern-Simons term, it does apparently seem to break parity, which is a big issue, because people don't expect the M2 brane to break parity. So that's an issue one has to think about.
Sorry, good morning again.
Yeah.
With the membrane, you wouldn't expect it to be conformally invariant for a small. I mean, it's only in the large n limit that you get a conformal theory for the non-trivial membrane, not for say 2.
Perhaps I should say this.
Yes, you do. You do expect it. For any number of membranes put on top of each other, you do expect it to be conformally invariant.
Why? If I just take one membrane, that's not conformally invariant theory.
Yeah, it is.
It's
It's
a
actually
free-
a theory.
It's a free theory. It's conformal.
I've got a cosmological constant on the brane.
Yeah, but
I've got L Planck, coupling to the auxiliary metric.
but isn't there some?
You take a flat infinite M2 brane, you're
Yes.
supposed to get a conformal theory.
No.
If you define it by n equals 8 super Yang mills just flowing to the infrared, SUN on the D2.
Okay, so if I just take the theory of membrane, the Nambu theory of the membrane, and then go to how Polyakov form, and so I get a theory of quadratic
Gauge fixed
scalars
everything
and
and it's
octaves,
nice
then
and flat.
I get L Planck on the brane. So there's a scale on the brane which is L Planck.
Usual D brane limit where it's just the gauge theory.
Yeah, but that's taking the L Planck goes to 0 limit. That's not the
Yes,
same
you
thing.
take the low energy limit.
Okay,
and then
so
you get a
the low
conformal
energy limit, yes, but he's not describing a low energy limit. He's meant to be describing the theory of
Well,
relativity.
I will.
The
It's
low
a
energy
spectrum
limit
of
is supposed to be super conformal.
The low energy limit, I agree. The low energy limit, I agree.
You can add a mass term to this, by the way.
Conformal, it's
No, the low energy limit, I agree, but he's not describing it as
Well,
low energy
no,
limit.
I think he is.
No,
I would like it to say, yeah. I mean, as I said that there's no free parameter, and here I got the brackets apparently because I haven't proven there's no free parameter. Just in this ansatz, you don't get it. But there is one free parameter, which is you can add a mass. So, for example, which I've just not included here, and it's not insightful. It's just a mass.
That's
M.
consistent with supersymmetry.
Yeah, it's certainly. Yeah. Well, at least it's consistent with the closure of the algebra. So I'd be very surprised if it doesn't preserve supersymmetry of the action.
All 16.
No, 16. So you add m psi bar psi plus m squared xi. So
How many masses?
just one. You need that because SO8 invariance.
There's some interesting sort of 11-dimensional gamma matrix between sides.
No, because it's got. You see, psi's already got an interesting gamma matrix. It's got gamma 0, 1, 2 on psi's minus psi. And that's the only gamma matrix that's consistent with the symmetries of the problem.
So is this super conformal then in terms of your algebra? Because you only had.
Well, yeah. Well, as a quantum theory, I cannot make any statements about this thing at this stage. But it's classically conformally invariant and it has maximal supersymmetry. So it's certainly a strong contender to be a superconformal field theory to all orders.
Or doesn't the superconformal have 32?
Yeah, but half of them are,
Non-linear.
well, they're these superconformal
Right.
generators. They're not the straightforward Qs. Just like n equals 4 super Yang mills, right? I mean, that's only got 16 supersymmetries in this language. Okay, so let me be a little bit more concrete, because so far I've told you about these algebras which I honestly don't understand that well. And you might say, well, there's none. But there aren't none, because there's one. And the problem is, of course, to go find large families of these algebras and take large n limits and do all that kind of stuff, which I don't know how to do. So the simplest case, of course, is to take 4 non-trivial generators. That's the smallest possible thing. So TAA equals 1 to n. And let me take H to be diagonal, in fact, proportional to the identity. That's the trace form. And you can actually do, and this is, you just need Gram-Schmidt or something. All I'm assuming is it's got positive eigenvalues. And then F necessarily has to be proportional to epsilon A, B, C, D, right? Because it's totally antisymmetric. And the important thing is F, A, B, C, this satisfies the fundamental identity. Okay? And if you want, but I'm not going to bore you with the details, you can realize this as a non-associative product, if you like. But like I said, with Wittgenstein's ladder, I don't want to necessarily think of it that way.
So, in principle, the algebra relevant to your problem should be labeled by some integer that gives you the number of branes.
Yes.
So what is
Well, I don't know because I only have one example. So how would I find it? I'd want you to give me a list of algebras like that satisfy this, and they'd have a dimension to them. But what's more important in the brane case is that the number of branes is the dimension of the Cartan subalgebra. So here I'd want you to give me a list of these algebras, and then the analog of the maximally associating subalgebras, and the dimension of that should correspond to the number of branes.
The dimension of the algebra should grow as n.
And then you'd like to see that the dimension of the algebra grows that number to the 3/2. That would be the prize. That would be the. Then you would surely all believe me. But right now, I think it's still this is a theory that certainly I don't think anyone would expect it to exist, and I claim it does, and I'm very confident about that. So what do you have if you go here? You can be a little bit more clear, in some sense. So let me define some tilted variables, which I've absorbed f into lambda and f into a, raised the index. Okay. So f here is just epsilon. Well, lambda tilde is just a generic antisymmetric matrix in that case, right? Lambda downstairs is a generic antisymmetric matrix, and this is invertible because it's epsilon. And this is also just a generic matrix, so it's just an SO4 connection. So A is an SO4, lambda is generating SO4, and from this perspective, X and psi are in the fundamental of SO4. They just have one index, and the gauge symmetry is matrix multiplication on a vector. And F, epsilon A to Z, is an invariant tensor of SO4. So in this one concrete example, this theory, you can just think of it as an SO4 gauge theory, where you use this invariant tensor to construct the interaction terms. And then you have to twist the Chern-Simons term here.
Consistent with it being a fuzzy S3. It's a particular representation. This is obviously an SO4 that acts on the.
Yeah. Well, again, the problem with when you're talking about fuzzy is you need to take some kind of large n limit, and that's what I don't.
Oh, you can be very fuzzy.
It's a very fuzzy.
And
S3.
then
It's
you
a very
can-
fuzzy S3. It's made out of 4x4 matrices.
Yeah, you could do that.
Yeah. Okay.
You said A is an auxiliary field, so what happens if you indicate it out?
Yeah. Well, naively, you'd land back on the model that we had last year, and you wouldn't see the supersymmetry.
In the specific example you just gave us, you should just give some normal known model. Just SO4 gauge symmetry, you know. There's nothing unconventional in the example you just mentioned.
Except this twisting here.
No, but this is auxiliary field. That's why I said if you integrate out the auxiliary field.
Yeah. Well, here the auxiliary field is required for supersymmetry, so I don't know what happens if you integrate it out. Yeah.
But I mean, typically, if you integrate out the auxiliary field, you just get an on-shell supersymmetry.
Well,
yeah, the
as I
action is
said,
still
this is-
supersymmetric, but the algebra clause is only on-shell. So
well, this only starts off only closing on shell.
Hmm?
This starts off only closing on shell. There's no off shell closure here.
The auxiliary fields do not modify the fact that an action is invariant, right? It only play a role in the supersymmetric algebra, not in the invariance of an action.
In this case, it certainly definitely does. This action will not be invariant without this term.
They'll give you nasty non-local terms.
And
Ely and Chern-Simons theory, they give statistical.
yeah,
versus
and this is not quite. I mean, it's not as simple auxiliary as just a scalar field with no gauge symmetry. I mean, integrating out means solving for f.
Solving for A, right? For
A, sorry, yeah. Which means inverting the derivative.
then it's not auxiliary. If
It's okay.
Is non-local, it's not auxiliary.
Yeah, I've called it non-dynamical. I don't think I've called it auxiliary. It's not dynamical, right? It doesn't have any local degrees of freedom. Okay. And certainly, I mean, you definitely need to have it in the action to preserve supersymmetry.
Question. You say it breaks parity.
No.
Could you have some different sort of parity that is preserved by these?
Yeah, we're looking into that, trying to see if we can get it. Okay. So that's the one. This is one concrete example, but it would be, I mean, wonderful to have wider classes of things. So what that really means is finding examples of this algebra, 3 algebras that satisfy this fundamental identity.
In this SO4 description, it is just an ordinary Lie algebra now based on SO4.
Yeah. So in that example, what happens in the SO4 case is these are just in the fundamental of SO4. That's in the fundamental of SO4. This is made out of the invariant tensor of SO4. And this is Chern-Simons term, but it's slightly twisted. So it's rather than being F wedge dA, it's F wedge dA with this antisymmetric tensor put in as well.
F wedge A, you mean?
Does it mix?
Yeah, F wedge A.
It mixes the two SO4s, or is it not? I mean, that
The two
SU2 subgroups.
It mixes the two SU2s. It's not diagonal.
You could probably define a parity.
Yeah, that's the sort of thing I'd like to think about. Yeah, is that by using F you could get an interesting parity definition. But yeah, so there's the wrong number of F's here. You see, this is on the. Remember, I defined the tilde variables, which was very simply the normal SO4 connection. Well, this is A tilde with A, and this is A tilde with A tilde with A, rather than A tilde, A tilde, A tilde, and A tilde, dA tilde, which is what would be the standard Chern-Simons term.
What is the divergence of the Chern-Simons term you have? So in other words, suppose you just took the ordinary divergence of it. What does that look like?
So if you.
So I guess.
Yeah, so it looks like something like, okay, rather than F wedge F, it's F little f wedge F. You see what I mean? So, right, you get F mu nu lambda rho A B C B F A B C B. Okay. Right. Are there any other questions? Well, I have a short section on some mass deformations, which I'll just briefly say that there's this work of Benner in which you turn on fluxes and you break SO8 down to SO4 and you preserve 4 supersymmetries. Then you get this puffy vacuum, and you can see that in this model, where the vacuum go like R squared with this particular formula. And the Myers type effect. Well, we can go back to our old model. Just go to the bosonic sector of the theory, where it takes this form, and we're using an n equals 2 language in 3 dimensions, because that's all the symmetries of the problem now. And this is the superpotential. That's what we wrote down a year ago. That should be a capital B. So in this language, it's very easy to add a mass term, because everything's manifestly supersymmetric, which is consistent with the symmetries. You can add more than this, you can be more general, but you add that to the superpotential, and you immediately see, of course, that the vacua, dw equals 0, correspond to this equation. So you've taken the fuzzy funnel and you've basically stabilized it, right, by adding a mass term. And these are your fuzzy S3 vacua. Now, this is related to one of your comments earlier there. You need, in this old language, without worrying about the 16 supersymmetries, you don't know what this kappa is, you have to normalize it. Well, let's normalize it so that you get the correct thing for the Basu-Harvey. And then if you look at these fuzzy sphere vacua, you get this formula. And this is off by 4/3 from the formula that Benner gives. So I don't know if that 4/3 is significant, because I don't exactly know what he means when he says M. Also, it's a classic getting 4/3 off in gauge theory versus black hole calculations. So maybe it's all okay even if it is 4/3 off, because one's supergravity computation at strong coupling and this is supposed to be a computation at the other end, although it's not quite clear in this case. But it's good that it reproduces, the correct M and the correct N scaling here. So this is working too. So I'll just finish with some comments and conclusions. So I certainly claim to have constructed a 3D field theory with 16 supersymmetries, SO8 R-symmetry, and no free parameters apart from a mass deformation. So classically it's conformal, so you might ask, is this dual to ADS4, crest size 7? But again, without being able to talk about taking large n limits, I'm sort of stuck here. Naively, parity is broken, but we would hope to do something about that along the lines people have suggested. And I certainly like to think that it's capturing at least some aspects of multiple M2-branes at a quantitative level. Right? But more work needs to be done here, and I guess the most crucial thing for me is to find more examples of 3 algebras with the fundamental identity. So there is one, so I'm not talking about an empty set. And I'd like to understand these algebras more. I mean, at first they look pretty weird, but certainly in the example, the simplest example, actually it's a SO4 gauge theory with fundamental matter. That's not weird. It's just been constructed in a strange manner. So perhaps all of them.
In that example, underlying there is a standard algebra.
Yeah.
So do you know whether this would always be the case, or do you know whether there is an abstraction to that?
I don't know. These algebras are kind of interesting because they're kind of like the square roots of the Lie algebra, right? The Lie algebra is generated by antisymmetric pairs. And then you do get what appears to be a standard Lie algebra. This action here is acting like a standard adjoint representation of some Lie algebra. Now, so I'm not sure if that means that there's always a Lie algebra generated by this, and that the x's are just in the and by definition the x's are in the fundamental representation, and then you're just a question of finding Lie algebras which have invariant 4 tensors. Maybe that's all there is to it. But it's slightly more than that, because the algebra has to be sort of generated by pairs, and that happens for SO4, but G2 has got an invariant 4 tensor, I believe. But I don't think you can realize G2 as antisymmetric pairs of its generators. But maybe you can.
But if behind that algebra there's always a normal algebra, there would be a more conventional construction without the need of this.
So you do it, but I mean, I've done it. This is the way I've developed it, because this is the way I was thinking. You start off, I need this antisymmetric fraud on it. It's a very complicated thing. And now I'm converging on it. Actually, maybe it's not very weird at all. And it would be nice to be able to say, no, I've got standard Lie algebras with extra structure on the fundamental representation. That I can easily believe is the case. In which case, that would be helpful, because you could presumably then delineate the list much more fastly than trying to imagine things from scratch. But there are lots of neat features. I mean, the other thing I'll mention, this triple product. One thing the fundamental identity tells you is that if I just fix one alpha, then I get a double bilinear product. And the fundamental identity says that this bilinear product does satisfy Jacobi. So these 3 algebras are Lie algebras, because you fix an element, you get a double product. But from the Lie algebra point of view, it's highly non-simple. So in the SO4 example, it breaks into SO3 if you times a line if you pick one element alpha.
So it breaks into what?
So
SL3 or SO3?
SO3 times a line, plus a line, plus a line.
Every 3 algebra implies a Lie algebra.
It gives a Lie algebra structure on itself in which it's not simple, because obviously this double product with alpha gives you 0. So alpha is a simple generator. So there's all these nice, cute statements, but I haven't. Whether or not they make sense in the whole, I don't know. So as was also raised, to make an identification between the elements of the 3 algebra and a physical M2-brane, you'd like to be able to say, well, these are the coordinates, these are the number. Presumably, you look for the vacuum states where everything's set. When you stick it in here, you get 0. But that means knowing what these things are like in more than one example. And there you might be able to see the n to the 3 halves coming out, because as we discussed, that's basically telling you the size of the analog of the Cartan subalgebra
Can I ask
as
another
a function
thing
of the
here?
dimension.
Can you replace SO4 with another real forms like SO1, 3 or?
Yes, you could. But the price of doing that would be that the Cartan, that this HAB would be whatever you chose it to be there, plus, minus, minus, minus. So then your action would not be normal. You get the wrong sign in the action.
So that looks like a curvature, right? You're acting in your AB with AB.
Yes.
Framing this as,
There is actually, I mean, there's a sort of a curious literature about these things, and one of them is there's an example by a Japanese guy, Kikuawa, who has something that satisfies the fundamental identity, and it is precisely the fundamental identity. Take a Riemann tensor with torsion. Look at the Bianchi identity, and suppose that it's coherently constant. Then the Bianchi identity is the fundamental identity on the curvature component. So there is a naive. That's the only difference there is it's not totally antisymmetric, but maybe you could restrict that if you want.
So about this n to the 3 over 2, because I'm still trying to understand why the representations of the fuzzy 3 sphere don't work.
Well, I don't know that they don't
With
work.
Neil Copeland, right, we showed that the n to the 3 over q came out from representations of the fuzzy 3 sphere.
What I meant to say that they don't work is I don't know that algebra satisfies the fundamental identity. So I don't know that you could construct these theories out of it.
So if I show that it obeys the fundamental identity, then that's you.
You have to remind me exactly what you had. How did you get the n to 3 halves coming out? Here I would need to show that the analog of the Cartan subalgebra, let's suppose that has dimension n.
Yeah.
Then I would want to show that the full algebra has dimension n to 3 halves,
Yeah.
large n in it.
That's what the fuzzy 3
That's what the
sphere
fuzzy
algebra has.
Okay,
That we
well,
showed.
excellent. Well, then please check to see if it satisfies the fundamental identity.
In your example, there's a you have x mu, and you said in that case there is a non-associative product that gives rise to your triple.
Yeah.
associator. What does that look like? X mu is what?
Yeah. So it's kind of ad hoc. It's the one that was in our paper last year. What can I rub off here? So just take matrices and take a preferred matrix Q and define A, B to be Q, A, B, Q. So this is matrix product, and this is defining a different product on matrices. Okay, it's a crazy choice, but I do it. A specific example, and then let's assume that Q anti-commutes with all the A's. The reason you want that is because if it commutes, then it associates. That's not important. What you then find, let me even be more specific. Think of the A's as four-dimensional gammas. Gamma 1, gamma 2, gamma 3, gamma 4. And Q, it seems, well, Q is the square root of gamma 5. Strange choice. But why do you do this? Because then you find that the associator, gamma I, gamma J, gamma K, because of the property of gamma 5 matrix, gives you epsilon IJK gamma L. This is defined as being the antisymmetrized associator. And the reason why we chose this and has this form is this is the one that reproduces Basu-Harvey's form, where you can also rewrite this as G.
That's exactly the n equals 1 representation of
Yeah.
the fuzzy 3 sphere.
But this doesn't,
I think you can generalize.
I wasn't able to get this to satisfy the fundamental identity and higher than 4. But maybe you have to choose special values. It's actually quite hard to satisfy fundamental identity. It's not, well, I don't know many examples, but I don't know many. I know one. And, there's another example, though, that's maybe relevant. Is this double Lambrou product, where you have functions on R3. This satisfies fundamental identity. but obviously it's an infinite dimensional example. So I've got like n equals 4 and I've got n equals infinity. But this is kind of intriguing because this is related to diffeomorphisms of R3, which you might think are related to what you get from a large number of M2-branes.
Sorry, one more thing. So what you had the kinetic term and ordinary potential for the membrane there, but what about the coupling to the I would say the C3 field? Because normally you should have the pullback of C3 coupling also, so you should have dx, dx, dx,
Yes.
Cijk, where C is the 3 form. Would you have that and keep your?
Yeah, you could add it. I don't know. I see what you're saying. There's a natural form for that. So you have Cijk, well, Ijk, and then of course you've got this product to soak up. So this like.
You'd want.
But you need.
You want derivatives in there, but
Yeah.
But fair enough, yeah.
Problem is that by itself, this term would, if you put it in the actions, would give you 0.
Yeah.
But just as in the D-brane case, you have a 2 form, and you put the commutator here. When you trace it out, it'll go. But if you had squares of it, you would get not something else 0. But anyway, I haven't included it. It's the bottom line.
One more question, sorry.
Yeah.
So if I took an open membrane, so then you might get dynamical degrees of freedom from this transition theory on the boundary.
Yeah.
Have you looked at that?
No. I've
Because
spent
that
my
would
last
correspond
few weeks
to-
trying to close this algebra,
Yeah,
making sure that every minus sign is not wrong, or every minus sign is right. Because
That will correspond to a non-abelian self-dual string, right?
yeah. Well, potentially there are lots of applications. If
And you can compare it with the anomaly calculation.
That would be interesting. That would be interesting. If you could even just see how many degrees of freedom you got there. Yeah. And presumably supersymmetry on a boundary would give you some conditions.
Yeah.
Which, I don't know, hopefully they would get some consistent boundary conditions.
Can I ask you a dumb question? If you suppose you found some 3 algebras
Yeah.
that implied a Lie algebra, and the Lie algebra they implied was SUN,
Yes.
does that mean that they would necessarily have dimension bigger than 2 halves?
Yeah, if it was of any end, then yes. Yeah, because then you know the Cartan. Well, actually you don't. You don't know, because you're not asking for the Cartan subalgebra of SUN now. You're asking how big is the space of where this associator vanishes, this triple product vanishes. So if it is true that these things are just Lie algebras with invariant 4 tensors, then the question is how big is the 0 space of the 4 tensor? And well, I have no way of telling you what that is.
Perhaps the fuzzy 3 sphere gives some idea about that question, because in that case you do have n by n matrices, n square degrees of freedom, but then to get a space that matches the spherical harmonics, you have to apply a projection. So there is concretely a projection, and that's exactly what leads to non-associativity. So the question here might be whether you can start with some big matrix algebra, have some sort of projection, and then have something that matches this product.
That does give rise to a 3 algebra, I suppose.
Well, no, the fuzzy, no, I don't know if it gives rise to a 3 algebra. It just gives rise to, the matrix algebra gives rise to solutions of matrix theory in various cases, the Basu-Harvey stuff. But that matrix algebra, from the point of view of a fuzzy sphere, contains too many degrees of freedom. If you try to expand all the matrices, that's why you need a projection. But then kind of trying to relate that structure to a 3 algebra, for example, that would probably.
David, your comment was that that projection actually gets you from n squared to n 3 halves.
Correct.
Yeah.
That's correct.
Yeah, well, I'll end with the comment then. So is this the world volume theory for multiple M2-branes? And if so, it would be the strong coupling limit. Since this is a conference on strong coupling somethings, I have to say something. Is the strong coupling fixed point of maximally supersymmetric 3D Yang mills. So that seems like a lot to hope for, but on the other hand, I think it is highly novel to have such a theory, at least classically. So thank you very much for your attention.
So you talked about three algebras. What about p algebras?
Well, you can, I mean, this all works rather generically. So you might imagine having a p product with the same definition of the fundamental identity and start having fun and seeing if you construct theories like that. You just wind up with a class of theories with, not much would change, I think, except that rather than having a potential in the scalars that's sixth order in the scalars, you'd have something that's a 2p order in the scalars.
Okay, let's not get late.
Yeah.